Good morning, everyone. In the last session, we were discussing some of the basic principles of the fermentation process, and we were discussing about various rate limiting factors in the fermentation process. In today's session, we will discuss in detail about the types of the fermentation process. The common meaning attributed to the term fermentation is that it is the conversion of a sugar into an organic acid or an alcohol. However, there is a broader meaning for the term fermentation. It is the intentional use of microorganisms such as the bacteria, yeast, and fungi to make products that are useful to humans, such as biomass, enzymes, primary and secondary metabolites, recombinant products, and products of biotransformation. So essentially, it is the use of microorganisms to make products useful to the humans on an industrial scale. And fermenters are classified with respect to several factors. Number one, feeding. It can be batch mode, fed batch mode, and continuous mode of operation. Number two, immobilization of the biocatalyst. Can be free or immobilized cells or enzymes. Number three, the characteristic state of matter in the system, that is submerged or solid substrate fermentations. Number four, single strain or mixed culture process. Number five, mixing of the fermenter, that is mechanical, pneumatic, and hydraulic agitation. And number six, the availability of oxygen. It can be aerobic, microaerobic, and anaerobic process. So the classification of fermenters is with respect to feeding, immobilization of the biocatalyst, the characteristic state of matter in the system, single strain or mixed culture process, mixing of the fermenter, and with respect to availability of the oxygen. Now, what type of fermentation process has to be implemented? The decision on which or as to which fermentation process should be implemented for a particular application is dependent on considering the advantages and disadvantages of each setup. To highlight a few points that has to be considered before deciding as to which fermentation process should be implemented. Number one, examining the properties and availability of the primary raw material. Number two, any necessary investment and operating cost. Number three, sustainability. Number four, availability of a competent workforce, which in turn is dependent on the desired productivity. And last but not the least is return on investment. So these are some of the important factors that has to be considered before deciding as to which fermentation process should be implemented for a particular application. That is examining the properties and availability of the primary raw materials. Is there any involvement of necessary operating cost? And what is the status of the sustainability? Availability of competent workforce, which is a dependent factor on desired productivity and return on the investment. So with this information as a background for understanding the fermentation process, now we'll try to understand in detail the types of the fermentation process. If you consider the submerged cultivation of microbial cells in fermenters, it guarantees a controlled environment for the efficient production of high quality end products and also to achieve optimum productivity and yield. Now the industrial fermenters can be in batch mode, fed batch mode or continuous mode, and they utilize variety of microorganisms which are capable enough to produce a wide range of products. So we'll try to understand each mode of fermentation process. To begin with, it is the batch culture. The batch culture represents a closed system in which the medium, nutrients and inoculum are added to the fermenter under aseptic conditions at the beginning of the reaction itself. Here the volume of the culture broth is theoretically constant. If you just look at this illustration, the inlet is crossed and even the outlet is crossed and the V is kept constant. That is, volume of the culture broth in the fermenter is theoretically constant. And the medium, nutrients and inoculum are added to the fermenter at the beginning of the cultivation itself. That's why the inlet and the outlet are crossed. And now we are saying that the volume of the culture broth in the fermenter is theoretically constant. Is it really true? There could be small deviations. Small deviations in culture volume are caused by a low feed rate of acid-base solutions for the sole purpose of maintaining the pH at desired level. Then by introducing air or gas into the culture. Such changes are usually ignored due to their small value relative to the total working volume. Right. So these are some of the small deviations which are not accounted in batch culture. Hence, the volume of the culture broth in the fermenter is said to be constant or theoretically constant, even though it is having small deviations which is insignificant relative to the total working volume of the fermenter. Typically, at the beginning of batch cultivation, a known number of viable cells are inoculated into the fermenter that is already filled with sterilized medium containing all the essential nutrients. So that is what it is said. The medium, nutrients and inoculum, they are added under aseptic conditions at the beginning of the reaction itself. Right. So if you consider the classical growth curve of the microorganisms, it is divided into 4 main phases. As the lag phase is inefficient phase of the culture, though the cells are metabolically active, they are adapting their physiology or the physiological process into a new environment. No doubt they are metabolically active, but they are trying to adapt themselves into a new environment. Thus, no significant increase in biomass concentration or the substrate consumption or the product synthesis are observed. So from fermentation process point of view, it is desirable to shorten this phase as much as possible. We call it as inefficient phase. The cells are metabolically active, but they are trying to adapt themselves into a new environment, and in this process there is no significant increase in the biomass concentration or the substrate consumption or product synthesis. So if you can minimize this inefficient period, then the target harvest will be more efficient. That is, the product harvest will be more efficient. The length of this lag phase, it is influenced by concentration of cells in the inoculum. See, our target is to reduce or shorten this inefficient period in the fermentation process. So what are the factors that has to be considered in order to shorten this period? So we need to understand what are the factors that are influenced in the lag phase. The concentration of cells in the inoculum and their physiological state, the composition of the inoculation, and the cultivation medium, be it the source of carbon and energy, the pH, the temperature, and finally the size of the inoculum. So these are some of the important factors that influences the length of the lag phase. If you want to shorten the length of the lag phase, so these factors have to be critically resolved. The concentration of cells in the inoculum, because the length of the lag phase is dependent on concentration of cells in the inoculum and their physiological state, the composition of the inoculation and cultivation medium, and size of the inoculum. So most industrial fermenter that are operated in batch mode due to relative simplicity of the process. So for efficient batch operation, it is important to minimize all non-reproductive steps or non-efficient steps so that you can achieve a higher rate of product synthesis, optimize productivity, and maximize the yield of the end product. Got it? So reduce the length of the non-productive, non-efficient periods in the growth curve of the cells, so that you end up with achieving a higher rate of product synthesis, optimize productivity, and maximize yield of the end product. Now moving on to the second mode of operation, that is fed batch culture. Fed batch culture represents a semi-open system in which one or more nutrients are aseptically and gradually added to the fermenter while the product is retained inside the fermenter. So if you can see the illustration, the outlet is crossed but not the inlet. That means the nutrients are aseptically and gradually added while the product is retained inside. Here the volume of the culture broth in the fermenter increases within the given time. The main advantages of fed batch over batch cultures are: number one, the possibility to prolong product synthesis. So these are the advantages of fed batch in comparison to the batch mode. Number one, the possibility to prolong product synthesis. Number two, the ability to achieve higher cell densities. Thus, there is an increase in the amount of the product, and the increase in the amount of the product is proportional to the concentration of the biomass. And number three, the capacity to enhance yield or productivity by controlled sequential addition of nutrients. So I have highlighted three important advantages of fed batch culture over batch culture. The possibility to prolong product synthesis. You can take up the product synthesis duration for much longer time when compared to the batch cultures. Then the ability to achieve higher cell densities, so that there is an increase in the amount of the product that is being synthesized, which is proportional to the concentration of the biomass. And the third one, the capacity to enhance yield or productivity by controlled sequential addition of the nutrients. There are many methods of adding a substrate to the fermenter. So it can be either as a concentrated solution of a sole carbon, or as a medium containing carbon plus other nutrients. So the proper choice of the nutrient feeding rate can enhance the culture performance considerably. So choosing the right feeding method or strategy can enhance the culture performance considerably, since it influences the cellular growth rate, the cell physiology, and the rate of product formation. Because in fed batch culture, it is feeding of the nutrients continuously. So the proper choice of the nutrient feeding strategy can enhance the culture performance to a significant level, and it influences the cellular growth rate, cell physiology, and the rate of product formation. The common feeding strategies are discontinuous feeding, achieved by regular or irregular pulses of substrates, and regular continuous feeding of nutrients, which are designed according to a pre-calculated profile. Can be discontinuous feeding achieved by regular or irregular pulses of the substrates, depending upon the demand for the substrate in the fermentation process. Or it can be a regular continuous feeding of nutrients designed according to the pre-calculated profile. Now, what is pre-calculated profile? So this is a beautiful illustration which depicts the relationship between the pre-calculated profiles of substrate feeding and specific growth rates of the cells. If you just look at this illustration, A is the constant feeding rate, and B is linear increase in the feeding rate, and C is exponential feeding rate. So in constant feeding rate, the cell growth gradually decreases, and in linear feeding rate, there is an increase in the cell growth, and finally the plateau is attained. And in the exponential feeding rate, the cell growth is constant. So the proper choice of nutrient feeding enhances the culture performance. You can have a constant feeding rate, a linear increase in feeding rate, or exponential feeding rate. Clear? Now moving on to the next mode of operation, that is continuous culture. Now the continuous culture represents an open system in which the nutrients are aseptically and continuously added to the fermenter, and the culture broth, that is which contains the cells and metabolites, is removed at the same time. Here the nutrients are aseptically and continuously added to the fermenter, and at the same time the culture broth, which contains the cells and the metabolites, are removed. Here the volume of the culture broth is constant due to a constant feed in and feed out rate. So you can observe here there is no cross for the outlet as well as for the inlet, and the volume is constant because of feed in and feed rate are constant throughout the continuous culture mode of operation. Nutrients are continuously added, and the culture broth, which contains the cells and metabolites, it is removed at the same time. Now continuous culture is used as a synonym for a chemostat, and there are other types of continuous operation such as turbidistat. Chemostat is represented by a constant specific growth rate of cells, whereas turbidistat is represented by a constant concentration of biomass. Chemostat is about constant specific growth rate of cells, and turbidistat is about constant concentration of biomass. The main advantage of continuous culture over the batch mode of operations are: number one, the possibility to set up optimum conditions for maximum and long-term product synthesis. Number two, the ability to achieve stable product quality. And number three, a distinct reduction in unprofitable, non-efficient periods of the fermenter operation. So, three important advantages of continuous culture: the possibility to set up optimum conditions for maximum and long-term product synthesis, the ability to achieve stable product quality, and a distinct reduction in unprofitable periods, as discussed earlier, of the fermenter operations. Right. There are disadvantages associated with this mode of operation. So this hampers the extensive utilization of continuous mode of operation in an industrial scale or on a large scale. Number one, increased risk of contamination due to the pumping of medium in and out of the fermenter. So these are some of the disadvantages that are listed in spite of having several advantages for the continuous culture operation. Number one, increased risk of contamination due to the pumping of the medium in and out of the fermenter. The danger of genetic mutations in the production strain in a long-term operation. And additional investment may be required, a possibility may be required for technical facilities. The first and second one are very much significant disadvantages: increased risk of contamination due to the pumping of the medium in and out of the fermenter, and the danger of genetic mutations in the production strain in a long-term operation, with additional investment that may be required in due course of the fermentation for technical facilities. Right. So moving on to the next category of fermentation is the solid substrate fermentation. The term SSF, or the solid substrate fermentation or solid substrate cultivation, it is used for systems where microorganisms are cultured on the surface of a concentrated water insoluble substrate. Till now we were discussing about the liquid medium. Now we are speaking about a solid substrate. That is, microorganisms are cultured on the surface of a concentrated water insoluble substrate. So usually it is polysaccharides as carbon source and energy source with a low level of free water. So what kind of microorganisms are usually employed? Filamentous fungi are preferable for the solid state fermentation process for the following reasons. Number one, due to their ability to grow on substrates with reduced water activity. Number two, due to their ability to penetrate their hyphae into the solid substrate. Number three, due to their ability to produce exoenzymes which decompose the polysaccharides, because polysaccharides are the main carbon source which are present in the solid substrates. Filamentous fungi are preferred for SSF due to their ability to grow on substrates with reduced water activity, their ability to penetrate their hyphae into the solid substrate, and their ability to produce the exoenzymes which are capable enough to decompose the polysaccharides. Right. So this table gives you a broad idea about the differences between a solid substrate fermentation and a submerged cultivation. Whatever we have discussed till now. In solid substrate fermentation, it is about the low water content of the cultivation medium, and it is a three-phase system: gas, liquid and solid. And the complex substrates are insoluble in water so that high local concentration of nutrients are available. And it is a non-homogeneous system, that is, gradient of nutrients are there. And microorganisms are grown on the surface of the solid substrate. If you compare these points with submerged cultivation, it is the liquid cultivation medium, that is approximately 95% of the medium is water, and it is a two-phase system, gas and liquid. Nutrients are dissolved in water, so the concentration of the nutrients is lower, that it becomes diluted, and it is a homogeneous system. Microorganisms are grown in the liquid medium. And in submerged cultivation, the transport process are usually not limited, and the transfer rate is between gas liquid. Cooling is achieved by the fermenter jacket, which has a pre-installed cooling system, and online monitoring and control of the process is a possibility, but the product is dissolved in the liquid phase. Contrary to this, in solid substrate fermentation, the limitations in heat, oxygen and nutrient transfer, there are limitations. Heat is removed by using a stream of air. Process monitoring and control are very much difficult, but high concentration of the product can be obtained. So these are some of the important differences between a solid substrate fermentation and submerged cultivation. So with this information, I'll stop my today's session over here. We'll continue in the next session with much more details on the process of fermentation. Thank you very much.